All right, ladies and gentlemen, let's take a look here. Um, let's see what's going on. Okay, we got the lecture here online for you guys. And I want to remind you, I think I did send you guys an updated version for your study guide. Okay, so I think I did. I sent it as an announcement to you guys. So I'm updating your study guide. So consider this draft 2. This may be updated tomorrow, but most of it will remain. So this should serve as a good guide. So I did send that to you guys, okay? All right, so that's there. And then let's see, what else do we have? Okay, I have this under higher order derivatives, but maybe we should change the title here. It's still higher order. Let's create here. Started to be, fall. Let's call this rates of change. Okay, rates of change, ladies and gentlemen. Okay, so let's kind of express to you guys why we even care about higher order derivatives. Okay, why do you even care? So we're kind of transitioning in a lot of ways to more of the applications of a derivative. Okay, so we have to focus on, okay, now that we know how to do a derivative, we know what it means. How do you apply it? So that's kind of the focus now. All right, you guys understand what I'm saying? So we want to focus on how to use this. It's just not a tool that's kind of, there's a lot of uses for derivatives. You can look at some of the uses to be graphical. There's a lot of graphical uses, and now we're going to look at some of the reasons why this was invented. Okay, so I'm going to give you guys here some background on this. We're going to say let S of t be a position function. Okay. It's a position function, and we think of it of a particle moving on a what? Straight line. S of what? T. S of t. And then t, what does t represent? T represents what? Time. So you have S of t, where t represents time. And then S is the actual position of the function. And we know we're going to start off with this idea of a particle moving on a straight line. So I got to give you guys a couple of definitions here just to kind of go over this. Definition of, well, we call it an average. In general, it's an average rate of change. We've got a general definition. But in this particular case, we'll just use this here. Okay? It's going to be delta S over delta T. And that's going to be the average rate of change over an interval. Where you have T1 and T2. Okay. So it's really average rate of, it's the average rate of change. Now, that's delta. Do you guys remember taking beginning algebra? You guys know, what is delta anything? This comes from this idea. I want you guys to know, where does this, yeah, this is, right? If you have y as f of x, this is the same thing. Delta y, delta what? Delta x. What was that from beginning algebra? That's what? y1 minus y2 over what? x2 minus x1. Wasn't that the slope? Yeah, well, it's your slope formula. It's a slope formula from beginning algebra. Okay, so this is from yeah, it's your slope formula. And that's your delta y, delta x. That's delta, that's change. And I think I put it backwards. I haven't had my coffee. I'm going to have to run over later to get my coffee. y2 minus y1 is x2 minus x1. So here you go. Here's the what? Slope. Now, what's delta S, delta T? What's that going to be? Same thing. S2 minus S1 over what? T2 minus T1. But for us, that's just kind of, this is the average rate of change as well in general. However, in particular, you can have an average rate of change for a position function. And we really call it the average what? It's really the average speed. Okay, so I really defined for you guys the average speed over an interval. All right, so for example, they can give you a particle. They can say, what's S of t now? S of t can be something like this. T to the fourth minus 4t plus 1, and they're going to give you a time interval. Let's say the time interval is going to be maybe from, we can say from 1 to maybe 4. Okay, so what this means here, generally speaking, for any position function, your time is greater than or equal to 0. Okay? S of t. So now they're just going to say, what's the average rate of speed? Or what's the average speed? Where do you go to get that coffee? Over the interval of time from 1 to 4. Okay? So here's again, this is going to be the T1, and this will be your T2. And notation-wise, sometimes they'll do this just for notation. They'll give you the S with a line on top for like an average, and maybe they'll give you like S of t. Okay, and then if you want more detail, that'll be S of t2 minus S of t1 over that difference in time. So this is the average speed, okay? So how does that look then? Here's the average speed. S is going to be what? S of 4 minus S of 1 over 4 minus 1. Okay, so you might say, well, how do I get S of 4? Well, plug in the value of 4 here. And here's what you're going to end up with. You're going to end up with what? 4 to the 4th power minus 4 times 4 plus 1 minus 1 to the 4th minus 4 times 1 plus 1. Okay? And then what is 4 minus 1? Do you guys know what that is? It's going to be 3. Is that true? Okay, so you get to just plug in these values. However, what's 4 to the 4th power? Do you guys know what that is? Should we get out our calculator? 4 to the 4th power. What is that going to be? Is that 256? So you get 256 minus 16 plus 1 minus, well, that would be minus 1 plus 4 minus 1 over 3. So you can do some of your arithmetic. So the average speed will be, maybe you want to use your calculator, I don't know, without our coffee here. So, I mean, it'll be, I can take a look at this. We don't need our calculator, but what is that going to be? 240. I think it's 243. Is that right? Double check. 241, 240, 243. 243 divided by 3, ladies and gentlemen. And I don't think that's divisible by 3. Oh, yes, it is. It is. Okay, good. It's a nice whole number. Yeah, it's 81. And they didn't give us any units. So we'll say units per, well, let's give it some units. Okay, let's really wake up with this. A lot of times they'll say, let this be in, I don't know, centimeters, and then T will be in terms of minutes. So we really got centimeters per what? Minute. Let's actually be very respectful of our colleagues in the sciences, right? Okay. So this is your average what? This is the average speed, ladies and gentlemen, over the what? Over that time interval, yeah. I mean, we're going to go into more of those details about this straight line business, but, you know, you're just doing you're just doing a very fundamental kind of thing. Is just, can you get if you have a position function, you do. Can you get the average speed over a time interval? Now, position functions, generally speaking, again, time has to be greater than or equal to 0. You don't have negative time. So you got this average speed definition, which is really the slope of any line, geometrically speaking. Slope between any 2 points on a curve from beginning algebra. And so this is your average speed over an interval. However, you might say, okay, Mr. Judge, that's great. We can get the average. However, what does this have to do with derivatives? Well, let's say, what's the instantaneous what? Speed. What do you think we mean by instantaneous speed? What is it? Well, it's the speed at an instant, but yes. So this is the speed at an instant of time what? T. And that has a what? Definition, instantaneous speed, okay? And I'm just going to go back and say there's a definition of an instantaneous rate of change. Okay? And that's going to be the limit as delta x goes to 0. So you have your average rate of change, and then you have your what? Instantaneous rate of change. Now, you might say, what is this? This is actually the definition of what? Of your derivative. This is really the definition. This is dy dx. Instantaneous. Okay, now you might say, well, is that y prime? Yes. Well, what's the instantaneous speed then? Well, very similarly, you'll have ds dt equal to the limit as the difference in time goes to 0 of delta s delta t. And this is going to be now s prime t. So here's my instantaneous speed, the speed at an instant. I'm sorry. Let me go back. I got to really be very careful with my language, okay? They want to know what's the instantaneous speed. Well, we'll see what that is. However, definition. This is really called the velocity function. Okay? V of t is defined to be s prime of t, where s of t is a what? Position function. And of course, t is always greater than or equal to 0. Okay, so I'm defining for you the velocity function v of t. There it is. Okay, now you said, why did I change the language from speed to velocity? Because, ladies and gentlemen, giving you guys more definitions, speed at time t, okay, that's defined to be the absolute value of the velocity function at t. Okay? So speed is the absolute value. So you got the velocity function, which is s prime t. You got speed, absolute value of that. So remember, this here is s prime t as well. No. Speed is defined to be the absolute value of something. So what that means, though, is you say absolute value. So I want you to make a remark here. This does mean that your velocity function can be positive, or it could be what? Negative. So if velocity is negative, that has meaning. If velocity is positive, that has meaning. But don't say velocity and speed are the same thing. You can't interchange those words. You say why? Because speed is what? It's the absolute value of what? Of velocity. Speed is usually positive. There's one exception, because velocity could be 0. And in the case that velocity is 0, ladies and gentlemen, speed will be 0. You see what I'm saying? So really, velocity can be positive, it could be negative, or it could be what? 0. And it all has meaning. And we're going to give you guys what the meaning is. Okay, so remember, we started off this definition this way. So let me do this here for you guys, right? You think of a particle. This is going to be, if we do this here. This is our location 0, and I'm going to call this S. Because what you're given always is what? This position function for a particle. And I want to point out to you guys an important thing, okay? You can be, your position could be positive or negative. You're looking at this as a real number line, right? So remember this, to the right is what? Positive, and to the left is what? Negative. This is just for your position. This is your location. All right, you guys okay with that? So what's really happening is you got this particle here. We can say the particle is moving on this line, and that's how they start this discussion. Remember, you're saying the particle is moving on a line. Okay, so it could be at a particular location, but okay, maybe this is time t. Sometime t, there's your particle. And your particle can do a few things here. Okay, I'm giving you guys some remarks here. The particle is going to either be doing one of 3 things. The particle will be moving to the what? To the right. The particle could be moving to the what? To the left. The particle can what? Not moving at all. It could stop. Okay, you guys okay with that? So either your particle is moving to the right, or the particle is moving to the left, or the particle is actually stopped. It's still. So what's the story here? When is your particle moving to the what? To the right, ladies and gentlemen. Let me share with you guys here. When the velocity is what? Positive. Your particle is moving to the left, and we can kind of show that. When your velocity is what? Negative. Okay? When is that particle still? Nope. When the velocity equals what? 0. Not position 0, But if your velocity is 0, you're not moving at all. Okay, does that kind of make some sense? So that derivative has valuable information about this particle and the direction it's going. Okay? That's the first derivative. Yeah.
So the original, like the line is the function itself, right?
No. The line is just, if we can call S, sometimes they write it this way. S is the position. S is your location. So in this first function here, let's say, what function did I give you guys? See this here? T to the fourth minus 4t plus 1. Okay. They can say, what is S of 0? Okay, now notice this is just asking you for the what? For the position. Is that true? So plug in 0. This is function notation. What are you guys going to get? You're at what? At 1. So you might say, what does that mean to be at 1? This is what it means. We're going to start to draw this here. This is your line S, I guess. So, okay, where is 1 on S? Right over here. Okay, so your particle is here when t equals what? 0. You guys okay with that? So that's kind of what you're looking at. This is a position function. So, today I want to give you guys a bunch of definitions so we can start to use this. This is called, by the way, initial what? Position. Position. Initial position. Is S of 0. Also thought of as your starting point. Okay, so we're looking at just the position. Graph that. And they might even say, what is S of 1, right? Well, just plug in what now? Plug in 1 into the position function, and what do you guys end up with? Don't you get 1 to the fourth minus 4, which is negative 3 plus 1? Isn't that negative 2? Okay, so you might say, well, where is negative 2? And that happens at what time? That happens at 1 second. Okay? So you might say, well, what just happened with this particle at that time? Well, obviously the particle moved in what direction? Right? Your particle in this time interval, out from 1 second later, the particle moved where? It moved to the left. Is that true? Okay, so you start at 1, and now you're at negative 2, 1 second later. This is, looking at position here. And let's do, what is S of 4? Because we looked at that. Well, plug in what now? 4. And yes, you had 4 to the fourth minus 4 times 4 plus what? 1. The other arithmetic we did in our head, so I apologize. 256 minus 16 plus 1. And you're now where? What's your position? 241. This is your location. Now, obviously, what happened here? I can't plot that location. That's off the what? Charts. Is that true? But maybe I'd say, okay, this isn't to scale, just so that I can share with you guys this. 241, okay? And what happens now? Your particle's over here. What's the time now? 4 seconds. So how did my particle, ladies and gentlemen, get to that location? Well, here's a simple answer. It must have turned around. And that's really the truth. It must have turned around and went back in the other what? Direction. Does that make some sense? Okay? So somehow, for some time, the particle turned around and went back in the other direction. But let me say this to you guys. There is some time t in order to do that. I'll do this now. Oh, it does do that. Nice. For some time t, obviously, your particle has to what? I don't know what that time is. But at some time t, the particle had to stop. Is that true? And turn around and go in the other direction. So, I mean, I know it kind of sounds weird, but if you're traveling in one direction, even anybody, to now end up in another direction, you have to stop and you have to now go in the other direction. Does that make any sense? Okay, this is why calculus was invented, to explain motion. So you're starting to look at why we care about these things like derivatives, second derivatives, even third derivatives, because we're starting to just describe something very simple, just motion. And calculus, these derivatives can do a lot of different things. They can describe the behavior of a curve, a graph, and that has a lot of meaning. As we've been seeing, vertical tangents, horizontal tangents. So we've been looking at how to really think of a derivative and how to use it, but we can use it in a lot of different ways. We could use it in a classical sense, which is to describe motion, which is why it was invented. So that's why I like to use this setting, and there's a lot of other settings, but I'm not going to use social science settings and blah, 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 blah. But ladies and gentlemen, that's the whole idea, okay? You got this position function that will tell you a location for various time values. But then you might say, but Mr. Judge, the particle was moving to the left, and somehow at 4 seconds, it's now at the location 241. So notice the information you're looking at. If t is 0, you're at 1. T is 1, you're at -2. But yet, at 4 seconds, you're at positive 241. So what's going on with that particle? It's moving, there's a speed, and there's even an acceleration. Because how could it get way over to a positive number 241 so fast? It had to have accelerated. Is that true? You guys see my point? You're looking at some amazing sort of things. So let me give you another definition, because you say, well, what does this have to do with my homework and higher order derivatives? Maybe this helps motivate you to do your homework.
Really?
Yes, it would motivate me. I remember when I was a kid, I was excited. Oh my God, acceleration, velocity?
You think they do that on like cars?
I used to, it's kind of an interesting thing. I used to watch, I was a kid. When my dad would drive, I used to look at the speedometer. I used to think that was interesting. And then I used to see the speedometer move. Anybody do the same thing? You ever, where the car's driving as a kid, you're looking at the speedometer move back and forth? You're like, whoa, what does that even mean? I don't know what that meant. I was a kid. That's kind of what we're talking about. You see, if your speedometer is still, you're traveling at a constant what? I'm going to say speed. It's constant. Let's say constant velocity for now. It's constant velocity. What if it's moving? You're accelerating. You're increasing your speed. That's a change in what? Velocity. So it's called acceleration. So if you're moving this, so just to kind of give you guys some fundamental ideas, the change in velocity over time, okay, and that's going to be, again, another limit. Okay, you go, what is this here? The change in velocity over time. Well, that's acceleration, ladies and gentlemen. So the car was what? Accelerating. So let me kind of move this out of the way. Okay, so the change in velocity over time is going to be your acceleration. So what am I really getting at? Acceleration is the derivative. This is defined to be, sorry, dv dt, which is acceleration. Okay? Acceleration is the derivative of the what? Velocity function. Yep. So this is acceleration. It's your acceleration function. Change in velocity over time, ladies and gentlemen, dv dt. Remember, this is v. Let me see if I can write it. I'm writing it. I want to be consistent, okay? And yes, you might say, hey, does that mean that this is really going to be what? The second derivative? The answer is yes. So in short, your acceleration is the second what? Derivative. Okay, it's your acceleration function. Now, your acceleration could be positive, it could be negative, it could be also what? Zero. You can have zero acceleration. And you can feel, in fact, you're sitting right now, and I hate to say this to you guys, you are feeling zero acceleration at the moment. You know, that's when your velocity is constant. You ever notice in a car, I'm going to put that as a note. Let's really be clear. Your acceleration can be what? Positive, or it can be what? Negative, or it can be what? Zero. Acceleration. Second derivative. You ever know anybody sit in a car and can you feel the motion in a car? If you ever notice this, maybe next time you're driving, you might feel, if you're seeing the speedometer, call it a velocityometer. If it's increasing, don't you feel your body moving in a particular direction? Yeah. Okay. And then what happens when that velocityometer stops? You feel what? What's supposed to happen is when that velocity stops, that's constant velocity. Say you're on the freeway, 60 miles per hour, you don't feel any motion. You feel stillness. But if the car's accelerating, you're moving in a direction. Okay? If it's decelerating, you're also moving in a direction. You guys see my point? So there is something called a constant velocity. That's acceleration will be zero when your velocity is constant. You say, how do we know acceleration is zero when velocity is constant? Well, if this is a constant number, what's the derivative of a constant? Zero. We're gonna work with these little details. Got to give you a lot of information. Zero acceleration, and then if you guys are really familiar with science, force is mass times what? Acceleration. So if your acceleration was zero, there's no what? No force. Force is zero. That's why you don't feel the movement. You say, well, how come if we're moving right now, and we're doing a lot of movement we're experiencing, how come we don't feel it? Part of the reason, not the only reason, part of the reason is because acceleration is zero. We're not accelerating or decelerating. It's constant velocity. But you don't feel stuff. Doesn't matter, you know. Anyway, we're looking at why calculus was invented. Okay. And yes, I did do a lot of worksheets. There's a lot of nice information on this stuff. Man. But I save it till now. You go, why do you save all these little details till now? Why don't you follow the book? You know, the book is a good book, but I find it to be a bit, what one want to say? You see the same topics over and over in like 3 or 4 places. And it's not that that's a bad thing. It's just a different philosophy. I would say, you know what, put it in one place. My personal feeling. Make it a little more concise. So you're starting to see here, ladies and gentlemen, some definitions come into play. Where's our graph here? This is just one function. But you're starting to see that, yeah, if a particle were to move, and it's not even thought of as being on a line, but you can. I mean, they do start with it being on a line this way. Obviously, it moved to the left and then stopped, because the only way you can go back in another direction is if you stop. Remember, this is instantaneous. This is at an instant, at a time value. You stop, and you had to turn back around. Now, you might stop and turn around again. This particle could have stopped in multiple places. We don't know. But you might say, how do we find when a particle stops? Well, that's when the velocity is what? 0. Remember we said that to you guys over here? When does a particle stop? When the velocity function equals 0. Stop and think about that. If you're driving a car in one direction, think of you're on a straight line, and you got to go back. You have to stop, really, and turn around. Is that true? Stopping means your velocity is what? 0. This is your velocity. Don't worry, this isn't going to be on your test. Well, I don't know if it's harsh. It's more of, are you up to date, or are you first learning about a power rule right now?
Yeah,
That's and there are some students that's why you don't see some students here. They're still they're at home. They got a study guide, and they're like, okay, now once I get the study guide, this is now when I study. And they go try to find a tutor somewhere, and they twist their arm, do my study guide, explain it to me. And it's like, this isn't driver's ed. You guys know, it's not as simple as driver's ed. This is like the real deal. I'll give you guys a little history so you guys know. This is the world I live in. I have to argue, debate, discuss. So I was at a meeting yesterday and doing so much of this nonsense. It's unbelievable, right? You know, if you guys do, or if you're familiar of Garfield High School and the Jaime Escalante, math instructor back in the 80s, and his work, I'm very familiar with it because I was one of his students, not at Garfield. He taught here at night for only 2 years. The only 2 years he taught, I had him here, 260, 261, 262, 263. So he used to fill us in on everything, And, everything that happened about the movie. I even remember there was what is that called? They had a screening. They had a premiere for the students, and he passed out free tickets. It was a whole big deal. And I remember my younger brother went to Garfield, actually. I was supposed to go to Garfield, but I had to be different. I'm always having to be different. Well, it was just like you had your mother go to Garfield, you had your grandfather go to Garfield. Now you're going to Garfield. And then my parents are divorced, and he moved close by. My father moved close by to be with his son, next to his sons. And I wanted to live with my father, so I did. And so he was in the Schur High School neighborhood. So I ended up going to Schur, which was interesting, coming from Belvedere Junior High, going to Schur. Yeah. Yeah, it's amazing. That's an interesting experience, you know. But my family's a Garfield High family. So anyway, and my younger brother, he's only like a year and a half younger. He was actually the star student, sort of. Between me and my brother, he was the kid who's was like, I don't know how to put it. He was higher in math than his older brother. I was a kid who, I didn't fool around. I wasn't a troublemaker. I'd rather read and play my guitar than do my homework. That's all. Not too different than a lot of others. But, you know, I don't even think he did his homework. But he was high. I guess he was able to survive. I don't know what. He was able to do a little bit better academically in high school than I did. But we both ended up here at ELAC because we didn't have any money. Our parents didn't have any money to send us to school. They didn't have any money. You know, we weren't going to any. My dad wasn't saving his pennies to send us to like SC or wherever, UCLA. That was not part of my childhood. You know, so he was an artist, kind of, you know, whatever. So we just had no money. So education and going to school wasn't in our plans. I was going to go in the Marines and that's it, you know. That was it. But anyway, my younger brother and the whole Garfield stuff, and I remember all of that at the same time, what was going on. It's a very interesting thing. And a lot of kids back then were trying to get bused because there was busing back then. They're trying to integrate students from different communities. And kids from the Valley were trying to get into Garfield High voluntarily just to get into the math program. And the irony about that situation is everybody hated Mr. Escalante. Everybody hated him. Okay, the parents of students who took his math classes hated him. The other teachers hated him. The world hated the man. The teachers union hated him. He caused so much problems and drama for not going along with the crowd. And you might say, why do they hate him? Well, because he would start an hour early every day, helping students with their homework, and an hour late after school for free. They had 2 periods of math, not 1 every day. So their focus was on doing the work. That was their focus, and that's what made everybody hate him. Parents said, "There's my son's spending too much time doing homework. You know, my daughter is spending too much time in your math class." Other teachers are mad because how come you don't study in my course? You guys get the picture? Everybody's angry with him. Why does the math program get the band room with the air conditioning? Well, because somebody donated air conditioning for the math program. So all the other teachers are angry too. They were like, how come you get the AC? And back then, nobody had AC. And it was hot in LA. So everybody was angry. Oh, those math students get all the research. Nothing's changed, ladies and gentlemen. But he made people do the work. You know, if you showed up late, I mean, what would he do? I mean, you couldn't show up not doing your homework. If you did, he'd throw you out. But you want to know the real reason he was successful? Because remember, if you're starting an hour early and ending an hour late and you're not getting paid, the union's mad at him. So they were mad. But do you guys want to know something about that situation? You know who was really behind the success of it all? Was the principal of the high school. It was an administrator. Because the administrator supported him, took all the heat, all the hate from everybody. Hate from the district, LAUSD hated him, the union hated him, parents were angry. He took all the heat. It was the principal. And they ended his career for that. His career was because of the success. Say, really? You're successful and you give up your career? Yeah, he didn't go along to Pelong. He supported, Jaime Escalante. So there's a lot of drama behind the scenes just for making people do their homework. That was it. So if you say, will it ever happen again? I'll say no. You say, why? Because there's too many people that don't have enough courage to do the right thing. They'll end their career, and they don't want to do that. And this guy's career ended. They banished him as a principal from LAUSD for supporting, Jaime Escalante for doing what he was doing. So that program ended, and it will never be what it ever was because of that. So it's interesting because all he was trying to do is tell people, do your homework. That's it. So sometimes you'll see now students who haven't done their homework, and they're not going to do well. It's a simple message. Nothing more. So it's kind of interesting to me that all I did was do my homework. That's it. Did my work when I was supposed to do it, kept up to date. I didn't want him to yell at me. I didn't want him to get mad. I came in, I was the shyest guy in the room, sitting in the front, and, that's it. Nothing more. One day after 2 years, students asked Mr. Escalante who was the best math student in the room. And you know what he said? Daniel Judge. That he's going to do his homework. He's going to succeed. And he said to me, major in math, you're good at it. I wouldn't have done it unless he told me. But because he told me, I did it. So I did. So interesting. But, you'll see, you put out study guides and you show people that you put out these resources, and yes. And unfortunately, do I blame those students? Not necessarily, because they just don't realize what they're doing. And sometimes they just don't believe me. They won't believe me. They'll study other things like, I'm going to put my chemistry first. I'm going to put my biology first. I'm going to put math last. And they have it backwards. They have it all wrong. You're just wrong. You're doing it backwards. And those students that have believed me have done very well. So it's going to be a question of, do you believe with what I'm telling you to do, when to do it, or do you not? And I don't take it personal if people don't do it. I don't take it personal. It's okay. It'll be a learning experience. So I've been doing this for over, 25 years now? I've been teaching it for 25 years, going through this for 25 years. I've seen a lot. Some of my own students have come back and they've asked me, Mr. Judge, what should I major in? Or they've asked me, I majored in math. I'm trying to go to graduate school. What do you think I should do? Right. I get a lot of that. And, it's interesting is that I say, oh, good. You majored in math. Right. That's wonderful. Why'd you do that? And I have been told by my own students, they said, because you told me to do it. So, sometimes you need somebody to tell you. And I don't even realize what I even said. I don't even remember. I said, you told me to do it. You said I was good at math. I said, oh, I did? So what you say is very meaningful to people. So it's an interesting thing, So what we're getting at now here with this problem, which I will put up the video, okay? I've been waiting to do that. Because what's going to happen, where's Shannon? It's her question. If you're listening, Shannon, I'm putting up that video soon because you know why? We're going to try to find where that particle stops. And you say, how do I know where this particle stops? I got to find the derivative of this function and set it equal to what? 0. And that's going to give me a polynomial that I have to do what now with? Solve. Hopefully by factoring, usually by factoring. In fact, most of the time if maybe even all the time by factoring. Okay? So this function now, what do we have to do? We have to get the what? The derivative. Okay? So we're going to work on all these great details here. So, how do you guys get that derivative? You guys remember this? What do you guys think you do here now? Notice the operator notation. Do you guys know what I'm saying? Use your properties. Oops. So what do you guys get? What's this going to be? 4t3. And then this is going to be what? 1. What is this? 0. So the velocity function is going to be what? 4t cubed minus what? 4. Okay. Let me pick this up. All right. So this is what you guys want to find. There's your velocity function. Say, okay, what do I do with this? They want to know then, for what time t did your what? Particle stop. Well, you set that derivative equal to 0, and you solve for what? For t. 4t cubed minus 4 equals what? Equals 0. So how do you guys think you're going to have to, what you're going to do with this now? What do you guys think you do? You're going to have to what? Factor. T cubed minus 1 is 0. Can you guys solve for t? How about this? T cubed is 1. Isn't t the cube root of 1? What is this? Is t 1? Guess what, ladies and gentlemen? Your particle stopped where? At 1 second. The particle stopped. This is where your particle stopped. So this is the details. And remember right in here, okay? What's the story there? At this point here, although I did not factor, but at this point, I use some what? Algebra. So why do you think Mr. Jaime Escalante came in an hour early? Help people with their what? Algebra. Why did he leave an hour late? Help people with their algebra. There it is. Well, if you divide both sides by 4, that's all right. We're going to help you with your what? Algebra, although I can't come in an hour early. I have to put up some what? Videos. So that you guys can get some of that. That's what they did. Yes. Yes. So if you said, Mr. Judge, I think I've seen this before. I'll see, I know you have. Because on a curve, this is the location where you have a horizontal tangent. Absolutely. You guys see how that works? Because of what? well, it's you're gonna see more in the future, but I should say it's completely analogous. What does that mean to be analogous? Similar to if you're looking for on a graph, where's the horizontal tangent? Same process. So this is why I say you guys have already done a lot of this. I just changed the letters and gave you definitions of what it means in a different setting. And that's it. So that's exactly what you would do for a horizontal tangent. And we'll see more. There's a lot more to see here. Positive slope, positive velocity, negative slope, negative velocity. What does that mean? The particle's moving to the left, particle's moving to the right. And, you know, we can prove it to you guys. We can show you guys this stuff, but it's doable. You guys can do this. If I could do it, anybody could do it. That's why I shake my head. Crazy. If I could do it, anybody can. And by the way, my younger brother, he became a big shot engineer for the gas company. Well, I don't know. He worked for JPL, and then he went to the gas company. He was one of these contract engineers and stuff. I don't know how much money he makes. I don't want to ask. But he probably makes more money than me. Younger brother. Anyway, he doesn't work as hard, though. Tell you that. He's not getting into heaven like me, though. No, I'm sure he is. I'm sure he is. I'll say that again. He'll get in, I hope. Who knows? But he does. It's true. You know, he's another ELAC student. You know, he went to Garfield, and there's a whole story there. He wasn't even at the Escalante camp. He was in the Ben Jimenez camp. And you go, who's Ben Jimenez? Well, you never heard of him, but he was also part of that program. Ben Jimenez was an adjunct here. I know Ben. There's a whole story behind, there's a lot of information behind that. So he was in the Ben Jimenez camp. I was in the Escalante camp. And they had a rivalry, let's just say. One person, it all comes, there's a lot more to the story. This is why you see the gear that you see. What I wanted to do is interview them and put this stuff online. I want the story out. But they declined. They did not want, it's too painful for them for a lot of reasons, not just, there's a lot of things that went behind the scenes that people don't know about. So they just don't want to relive it. When I say, you guys have a great story, what the hell? You got to get your story out there. For some of them, it's just still too painful years later. Anyway, okay, I put your stuff online. You guys know the drill. I'll see you on what? Monday. Have a great weekend. Take care. Stay safe.